Okay, so we're going to go through section 11.8 and then a little bit of 11.9, but not very much from 11.9. It's just a couple techniques. So this is called power series. So we had an introduction to power series in class just the other day, but let me just remind you what a power series is. So a power series is just a function. Maybe we would denote it as p of x. It's a series of the following form. So n0 to infinity, cn x minus a to the n. So this looks like c0 plus c1 times x minus a plus c2 times x minus a squared plus and so on, okay, forever. And here, a and all of the CNs, these are supposed to be in the real numbers. So these are real numbers or real expressions of some kind. They're supposed to be in the reals. And A is called the center of the power series. And the CNs are called coefficients. The coefficients. So very typically, there's usually a formula for the CN. So usually there's a formula given. All right, so we saw some examples. So let's take a look at just a couple examples. We had this series here. So this is 1 plus x squared plus x cubed, and so on. Here the center is 0, and the formula for the CNs is each CN is just 1. Okay, so there was one example. Another example we had was, so how about n factorial x to the n, starting at 0, going forward. So the terms here look like 1 plus, well, maybe we'll write it like this. It's 0 factorial, which is equal to 1. Plus 1 factorial times x, plus 2 factorial times x squared, plus 3 factorial times x cubed, and so on. Here, our formulas are, let's see, so A, the center of this thing is 0, and the formula for our CNs is just n factorial, like this. Okay. Now, let's take a look at another example. So there's a start. I guess we don't have to start at 0, but we'll start here at 1. So we have minus 1 to the n plus 1 power, x minus 3 divided by n, to the n power. So this, so here in this case, so we're starting at 1, so we get x minus 3 plus minus, because the next term is a minus, x minus 3 squared over 2 plus x minus 3 cubed over 3 minus, and we'll do one more, x minus 3 to the 4th over 4, and so on. Here, the center of this series is 3, so it's a little bit different. The formula for C0 is just 0, because there's no 0th term here. And then for Cn, when if n is bigger than 0, the formula for Cn is minus 1 to the n plus 1 over n. Okay, so these are our coefficients. The coefficient, this is the first 0th coefficient is 0, and if n is bigger than 0, then the nth coefficient is that formula, and we have this. Okay, so there's a theorem that we mentioned last time. This theorem says that for every power series, exactly one of the following things happen. So exactly one of the following situations for a power series happens. So this is our power series is Cn x minus a to the n, and starting from 0 to infinity. So this is our power series. So 1, either the power series converges only for x equal to a, the center. Okay. In this case, well, I mean, take a look at what this series has to look like. So P of A, this is our power series. So when you plug in A, all of the terms here are A minus A. So the only term that shows up will be C0, okay? So this is the convergent value. In this case, P equals C to A is the convergent value of the series. The series. And we say the radius of convergence is 0. Right. Okay, 2, the series converges for all x values. Okay. And this means, so in this case we say the radius of convergence is infinity. Okay, so what that means that, so in case number 1, the only number for x that you can plug in that makes this convergent is when x is equal to a. And so that's the only convergent value is when the series converges only at the center. Or you might be able to plug in any value of x and have this be a convergent series. So if the series converges for all x values, we call the radius of convergence. So this is 1 or 2, and then there's an or, and we have to do 3 on the next page. So there's one other circumstance, or, so this is or 3. There is a positive number r, and this is the radius of convergence, where the power series P of x converges if x is in the range, basically if x is within r of the center. So it's in the range, so here x has to be bigger than the center minus r, and it has to be less than the center plus r. Okay, so on a number line, this is what this looks like. Here's the center of the power series. Here is a minus r, and here is a plus r. So this distance here is supposed to be r, and so is this distance here, r. So that's what this is this region. So what this means, so there's a positive number where P of x converges if x is in this range, and diverges outside. Diverges if x is bigger than a plus r, or x is less than a minus r. Okay, so that means that it diverges. So this is the converges case right there, and then this is the diverges case. So here's a minus r, here's a plus r, and it diverges here. Okay, so there's a positive number r where the power series converges if your x value is that is within r of the center, and it diverges if you're outside of that range from the center. Okay, and we have to check by other methods the case. So the case is when x is equal to a plus r, or x is equal to a minus r. Okay. So that is the statement of the convergence for power series. So I'm just going to review this with you really quick. So exactly one of the three following things occurs for a power series. Either it converges only at the center, or it converges for all x values, or it converges for a small window or window around the center. Okay. So how do we do this? How do we determine which? And the answer is the ratio test. Okay, so we're going to go through some examples right now to figure this out. So let's look at some examples here. So example, and this is how the question will be phrased. Determine the radius of convergence of the series, let's do x to the n goes from 0 to infinity. The radius of convergence of this, including the endpoints if necessary. Including the endpoints of the interval of convergence, if necessary. Okay, so this is exactly how the question will be asked. Okay, so solution to this. So we have this tool at our disposal, the ratio test. So we're going to use, we're going to take this here, this expression here, and we're going to use the ratio test. So if we think of this as being a series that we're going to apply the ratio test to, then that means that a(n plus 1 is just x to the n plus 1, and that means that a(n) is just x to the n. So let's take the limit of these. So if we take L equal to it's the limit as n goes to infinity of the absolute value of a(n plus 1 over a(n), then this is equal to the limit as n goes to infinity of x to the n plus 1 over x to the n. Okay, this is we're thinking of it as a series that converges, and we're testing it with the ratio test here. So now x can be a negative number. Okay, and so we have to keep these absolute value symbols here. But let's just take a look at what we get here. So we have n plus 1 copies of x here, and n copies of x here, and so they cancel and leave us exactly one copy of x. Notice no more n's here. Okay, so that means that the limit of this as n goes to infinity is just the absolute value, because there are no n's. So this is because no n's. And we're taking a limit, right? This thing is just absolute value of x for every value of n. And so the limit is this. So that means L is equal to the absolute value of whatever number you're plugging in. And we want convergence. So we want L less than 1. Okay? So that means that we take the absolute value of x to be less than 1. This is saying that if the absolute value of x is less than 1, then L will be less than 1. L was this limit, and the ratio test guarantees our convergence there. So if x is less than 1 in absolute value, then we have convergence by the ratio test. Okay? So what does that look like, x less than 1 in absolute value? x less than 1 in absolute value is this picture. Here's 0, that's the center. Here's 1, here's minus 1, and so we're looking at this interval here. So this is our convergence. This is the range for convergence. So it's x is bigger than minus 1 and x is equal to 1, and x is less than 1. So this is our range. The radius is equal to 1. Okay, this is the radius of convergence around the center. And so what about when, so that means that we have to check these endpoints. So what about the endpoints? Okay, so the endpoints of this are when x is either equal to minus 1 and x is equal to 1. So x is equal to minus 1, x is equal to 1. What do we get in each of these cases? So here we get minus 1 to the n, and goes from 0 to infinity. And here we get 1 to the n, and goes from 0 to infinity. Okay. In this case, starting off at 0, we get 1, minus 1, plus 1, minus 1, plus 1, minus 1 forever. Okay. This diverges, right? Because it's just 1, and then you add the next term, you get 0, then you add the next term, you get 1, then you add the next term, you get 0, then you add the next term, you get 1. So this doesn't converge to any value, so it diverges. And here, this is just 1 plus 1 plus 1 plus 1 plus 1 forever. So this also diverges. So they diverge in different ways. This one gets larger and larger and larger. This one, the partial sums just don't approach a value. Okay, so that means that the actual so this power series, starting at 0, going to infinity, x to the n, converges on the interval from minus 1 to 1 and diverges everywhere else. So for all other x values. Okay. So this is your answer. There's your interval. The radius is 1. This is your answer. Okay. Let's go through another example. Okay. How about, let's take a look at this example that we just listed here. So n factorial x to the n, starting at 0, going to infinity. So this is, so here are an plus 1, okay, determine the radius of convergence. Okay, including the endpoints. So an plus 1 in this case is n plus 1 factorial times x to the n plus 1. An is n factorial times x to the n. And so L, which is the limit of the absolute value of the n plus 1 term over the n term, is, so here we get n plus 1 factorial times x to the n plus 1 over n factorial times x to the n, like this. Now, we get some canceling here, and so let's take care of that. So there are n plus 1 copies of x and n copies of x here, so that leaves us with 1 copy of x in the top, and then there were n factorials down here, and then n plus 1 factorials right here, so that leaves us with n plus 1 in the bottom. So here, down in the bottom, we just have 1s. So this is the limit as n goes to infinity of the absolute value of n plus 1 times x. Sorry, that was just a scribble. Okay, now, n plus 1 is always positive, so let's just take this right out here. So this is the limit, so we have an n plus 1 here, and then that leaves us with an absolute value of x right here. Now this absolute value of x isn't changing. It doesn't depend on n at all, and so we can take it out of this limit here. And we're just looking at the absolute value of x times that limit. Okay. Now if you think about this, well, no matter what the value of x is that you plugged in here, this is going to go to infinity. So this is infinity. So L is equal to infinity, which is most definitely bigger than 1. And so there is no value of x that you can plug in here that makes this converge. Okay, so therefore the power series converges only at the center, which is when x is equal to 0. Okay, so notice that this whole calculation, the only time this limit is not infinity is when you chose the x value of 0 from the start, okay, which was the center of the power series. So the power series converges only at the center x equals 0 and diverges elsewhere, and diverges for every other value. Diverges otherwise. So here the radius of convergence is 0. Okay? So this is an example of possibility 1 from our theorem about the convergence of power series. Okay, let's do another example. So how about the value x to the n over n factorial? So this looks similar, except now the n factorial is in the bottom. So this is 0 to infinity, so this power series looks like 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So here the center of the power series again is 0, and the coefficients, our terms for our coefficients, are 1 over n factorial here. Now if we want to use, so the question is, determine the radius of convergence. Then we can do that using the ratio test. So here is our solution. So we have L is equal to, I'm going to just skip over the n plus 1, the a's at this point. So we're just going to use our general strategy, which is you take the n plus first term, which is this, divided by the n term, which is this, okay? And we simplify this, okay? So there's an n factorial and an n plus 1 factorial. In the denominator and in the denominator here, so we get the numerator, and then we have, this is times x to the n plus 1 over x to the n. Okay. Again, more simplification. So we have, so this quantity right here, the n's, is all positive, so we don't care about its absolute value. There are n factorial here and n plus 1 factorial here, so we get 1 over n plus 1. As in the previous example that we've seen. And here we have one extra copy of x in the numerator, and so that appears as an absolute value of x in the numerator. The reason why we keep the absolute values on the x's here is because x can be any number. We're testing for any number here, and it could be negative. And so we need to preserve that absolute value. So, but on the other hand, as in the last example, this term does not depend on n, so this will always happen, that the absolute value comes out of the limit, and then we're just taking a look at this limit right here. Well, 1 over n plus 1 goes to 0 as n goes to infinity, so this is equal to 0. Doesn't matter what x is, this is the absolute value of x times 0 in the limit, and so we get 0. So this is definitely less than 1, and so the power series x x to the n over n factorial converges for all, so for all x, so the radius is infinity. Okay, so this converges for, you can plug any number you like in there for x. Just as a matter of fact, this series here turns out to what it converges to. So if you take so 1 plus x over 1 factorial plus x squared over 2 factorial plus and so on, this converges to e to the x. Okay, plug in a number here, take this infinite sum, the number it's getting closer to in the sum is e to the x. This is just a fact, we'll see this later. Okay. Perhaps one more example here, and let me just check. I am getting pretty close to my time limit on this video, so we're going to do a very, very quick example. Same thing, minus 1 to the n plus 1 over x minus 3 to the n over n. This is our previous example starting at 1 going to infinity. Find the radius of convergence. So we take L, our limit, n goes to infinity. So I'm going to do the n plus 1 term. Now remember, we're taking absolute values, so you can forget all about the minus 1s that occur here. So minus 1 to that power, just ignore it, doesn't even matter. X minus 3 to the n plus 1 divided by n plus 1. That's the first term. And then the second term, x minus 3 to the n divided by n. Okay, here we go. We take our algebraic judo, and we have an n over n plus 1. That's what the n plus 1 and the n cancel to. And then we have x minus 3 to the n plus 1 over x minus 3 to the n, like this. Okay, again, this will n over n plus 1 is always going to be a positive number, so we can take that right out of the absolute values. And here we have one extra copy of x minus 3 in the top. And so this fraction here just becomes the absolute value of x minus 3. As we did in the previous examples, the absolute value of x minus 3 does not depend on the letter n. And so we're really just taking this limit here. So the limit of this, we all know by now, n over n plus 1 approaches 1 in the limit, and so this is x minus 3. Okay, so now we have to check. For convergence, we need L to be less than 1. So we want the absolute value of x minus 3 to be less than 1. Well, what that means that on the number line, here's 3. We want the distance from 3 to be less than 1. So we have 4 and we have 2. So this is our interval of convergence. Okay? So x being between 2 and 4 is the interval of convergence. And the radius is 1. And so we have to check now. Wow, I'm out of paper. So now we have to check when x equals 4 and x equals 2. This is the last thing that we're going to check. So what I want you to do is I want you to do this as an exercise. Since I'm going to run out of time on my video here, I've got another pad of paper. So when x is equal to 4, the series that we get is the following series. So we're starting at 1, counting to infinity, minus 1 to the n plus 1, and then we put in 4 for x. So we have 4 minus 3 to the n power over n, like this. So this is really minus 1 to the n plus 1 times, well, 4 minus 3 is 1. 1 to the n is just 1. And so we get this series here, okay? This converges by the alternating series test. Okay, so that means that x equals 4 gets included. X equals 2, we have minus 1 to the n plus 1 times 2 minus 3 to the n over n. So simplify this out. This is a minus 1 now raised to the n power, and here we have a minus 1. So this is minus 1 raised to the, okay, we have to add these together. We get n plus 1 plus n is 2n plus 1 divided by n. Okay. What does this look like? This is always an odd number now. So that means that our sum looks like this. So it's minus this whole thing. So this is minus times 1 over n. Okay? And this diverges because the series of 1 over n diverges. So certainly minus times that diverges. So the actual interval of convergence is this. We include 4, but we don't include 2. So include 4, but don't include 2. Okay, we'll do more examples like this in class.